Okay. Hello and welcome to CIC Start Online webinar here at Glasgow Caledonian University. My name is Branka Dimitrijević and I will moderate today's event. Our seminars and webinars disseminate the outcomes of feasibility studies and academic consultancies undertaken through our project. The project supports collaboration of 7 Scottish universities and Scottish small to medium-sized enterprises in developing and testing innovations for more sustainable building design and refurbishment. The project is funded by European Regional Development Fund and CIC program of Scottish Government, which is currently managed by Scottish Funding Council. This is a live event, so if there is a fire alarm, we will have to stop and continue later, but you can join us or you can watch the video recording of this webinar a few days after the event. We plan to finish presentations around 1:30. You can start using chat facility to ask questions at any time during the webinar, but we will start answering the questions around 1:30. The webinar will close around 2 o'clock. If we do not answer all the questions, then the answers will be sent by email to the viewers later. So, the title of today's webinar is Developing Homegrown Natural Fiber Insulation Products, and we have quite a few samples here today with us to show them and to talk about their properties today. The speakers are Dr. Paul Baker of Glasgow Caledonian University and Bruce Newlands of Kraft Architecture. So I would kindly ask you now, Bruce, to start with your presentation.
Thank you, Branka. I'll start off with a very short presentation, a little bit about Kraft, just what we do. We are a very small practice. We are based in Glasgow, and we're involved with a number of building projects, as architects do, but we also do what we describe as research as well. We look at different product development, ranging from, in this case, insulation products, but we also look at off-site timber frame and other such products. The types of projects that we're involved with include the BRE Visitor Centre, where we're the architects for that project, and also a plot on the Fife Innovation Showcase, where we're demonstrating affordable housing going forward into 2013-2016. Our interest in natural fibre products really comes from, an architect's perspective, and that we know that there's products out there that exist. We also know that there's a variety of new products coming onto the market. Hemp has been something that is quite an age-old product, in many ways an age-old material, but has been used in quite innovative ways through various different procedures. Clearly, sheep's wool is a fantastic product on the market. There's a variety of manufacturers of that, and there's also wood fibre increasingly as well, used specifically in timber frame construction, I guess. And I guess that's our particular interest, timber frame, particularly for affordable housing. So what we kind of set off to do was to try and look at, well, what other fibres could be used to create natural fibre insulation. And in the back of our mind, or often how we set off in our product development projects, is that we look at the kind of legislative structure that surrounds us, what controls how we use products, and what might be, future scoping, you might describe it as. So in Scotland, Zero Waste Scotland is an initiative brought by the Scottish Government that aims, I think it's by 2020, to have zero waste throughout all forms of manufacture in Scotland. That obviously presents a big challenge, but also an opportunity as well. So we took that idea, and with the natural fibre idea of doing products, and we approached, in the first instance, Scottish Enterprise, and together with looking at a timber frame design, a very low energy timber frame design, we applied for a SMART award. We were successful with that. This was about 2 years ago, And really that was the genesis of us being able to try to prototype various different types of fibre for insulation purposes. Our first port of call, I guess, is probably the most obvious thing, is wool. But again, looking at the cycle, where is the wool fibre? Clearly, you can buy wool in terms of fleece, but we started looking at waste streams. Where was there actually waste wool streams? And there's surprisingly quite a lot in Scotland alone. Principally, we've looked at Scotland because there is quite a high percentage of woolen mills, but clearly there are other concentrations in the UK in terms of Bradford and the Midlands as well. But we really focused on Scotland. In some basic, figures from SEPA to show kind of textile and leather wastes throughout Scotland identifies many, many tens of thousands of tonnes of material. Now, that identification of material, in this case it's between 2006 and 2008, is fairly constant, but also that includes post-consumer waste, which is something that we didn't necessarily target to begin with. We were looking at mainly post-industrial waste or factory floor waste in order to use, because that's clean, it's ready to be processed, so it requires less pre-processing before we take it to look at manufacture. It's just another iteration of the product. So you can see there, in terms of textile and leather, you're up into 40,000 tonnes annual. To give you a little bit of an idea, a new build house, perhaps a 2013 specification house, might use as much as 3/4 of a tonne in the house itself. That includes not just for thermal applications, but acoustic applications as well, in terms of interfloors, party walls, and also partitions between rooms as well, which again, the regulations are asking for this type of performance. But you can see that there's an awful lot of tonnage. What we also looked at this time is we extended our search to look a little bit at wood and paper or cellulose as well. See tonnage, clearly a lot more tonnage. Generally that can be attributed partly to that it's often wet waste as well. So you are weighing water rather than dry fibre, let's say. So you have to kind of take the figures with a little pinch of salt when you're looking at them. But clearly, an awful lot of material out there that could potentially be used for making some form of lofted fibre product. So from that kind of point, and through this smart process, we effectively engaged with a number of different people, mainly a business case advisor, who helped us identify potential suppliers. I also knew of a local supplier close to where I was brought up in the north of Scotland, where I could source rags or shoddy very, very quickly. So what we started to do right away was to speak to various machine manufacturers, really in an effort to trial these different fibres. And the first fibre we trialled, and I guess it was a little bit extreme, was cashmere fibre. Not everyone can say they've got a cashmere house, I guess, but it's an interesting fibre. Surprisingly, there's quite a lot of tonnage of it. It's quite a processed fibre. Generally, we were accessing what's described as selvages, so it's kind of trims, I guess you might describe it as long trims. And the image that I'm showing on the screen there is effectively how you might purchase it from the wool mills itself, i.e. in uncompressed bales, which are not very efficient to ship, but that's what's coming out as a waste stream out of this particular wool mill. In this particular slide, what I'm kind of showing here is we teamed up initially with a French machine manufacturer, and one of the first trialling efforts we did was to ship 1/4 of a tonne of cashmere fibre to their prototyping plant based on area effort so that they can show off their machines and you can test products on. This is 1/4 of a tonne of cashmere waste, what it actually looks like, which gives you a little bit of an idea of the bulk that we're talking about here. Clearly this is uncompressed, and we'll talk through the process in a second about how you go through this process. If we can maybe look at video 1 at this point. This, basically, the simple process that we go through first is described as a tearing process, and effectively you're taking these long lines of rags and processing them into a much smaller fibre. This is the type of machine that might be used for that process. Pre-built machine, pre-made for these types of purposes. It's not necessarily a new technology, it's a known technology, but it is important, the kind of quality of the machine and the tearing teeth of the machines, etc. as well. And effectively, what comes out the far end of that machine when you put the small scraps in might be described as cotton wool. It's a fibre that has been torn right down into a particular size and consistency, ready to be compressed and baled to make a much more efficient means of transporting it in a factory condition. That's it as a baled fabric. So you clearly, as the unbaled bags of fabric, very, very space intensive, you might describe, to something that's a baled fabric. This is the type of bale that might be bought on the market as well. Different people offer this as a pre-processed product. The process itself is actually quite simple, quite a linear process. In our case, we looked at an air-laid thermobonding process, and what that means is that effectively that fibre we mix with a binder, which I'll discuss in a second. That blend of fibres is then laid in layers by a special machine called an air-lay machine, and then that product, that very aerated product, is put through a bonding process, which is effectively an oven that melts the binder and then forms the actual product together. Very, very flexible process, lots of parameters, and that you can dictate the depth of the material, the depth of the product. You can dictate the density of the product. It's something that Paul's going to touch on with the research that he's looked into, how that might affect things like thermal conductivity, but also things like resilience as well, because apart from creating insulation, the line could also create resilient mats, for instance, for underfloor applications. So again, you can probably look at that in more detail when you can download the presentation, but a fairly simple production process, a linear process. And I'll just kind of talk you through how the process then continues. So those bales of fibre that we produced go into a very simple hopper process. This one on the left is the cashmere fibre that's actually being put into the hopper. The hopper on the right contains this white material, which is described as a bico fibre. It's effectively a technical textile. It's got a large polyester content, all polyester in fact, but it's got a dual core sheath. So really it's a fibre designed to melt at a certain temperature, but to maintain its strength within the fibre. As a kind of quick idea, the quantity of that fibre, that binder fibre, varies depending on the main source fibre. So it can be, in some instances we've looked at, can be as low as when I go through the different products that we've prototyped. That's a kind of close-up of that fibre. Again, generally bought as a staple fibre on the open market. There's various producers, there's also various qualities and particular specifications for that particular fibre, but it's the key component of any thermobond product. And there is the kind of quite simple mixing at this stage. You can see the kind of percentage there. I think in this particular prototype we were looking at about 10% binder fibre within the main fibre. That mix of fibres is then processed through the air-laid system. So effectively the air-laid system is blending those fibres into a very homogeneous mix, and then actually laying those fibres into a mat form, ready to be bonded or formed in the ovens. And if we maybe play video 2, the process, once it's been formed, is a very simple process where it comes out. You can see that it's a very light material when it's being moved there. The fibres are loose, effectively, they are not bonded yet. So it's really just a very homogeneous mix of fibre, almost still like cotton wool, but aerated. Because it's been laid in airs, you've basically created air within the fibres themselves and between the fibres as well, which is clearly an insulation product by its nature. In this case as well, an interesting part of the process, these two quite dangerous looking sharp discs either side of the process, are quite interesting because they clearly shape the product as it comes out of the process, but what they also tell you that this is a zero waste process. The material goes back into the production from that point on, so there is no waste in the process when you're producing it. You also, as you can clearly see there, end up with a very homogeneous felted type product, which is a little bit different from, say, mineral fibres that you might see that are much more striated. That striation has a benefit in that you can tear those particular insulation products apart if you're on site and you need a thinner part. We were kind of conscious of that as part of this process, but we made the decision that the quality of the homogeneity of the product is actually a key factor in what I think would be a successful product, especially for timber frame, particularly timber frame walls. That gives you a little bit of idea of the scale. This is clearly only a prototyping plant, but the large machine in the foreground here is effectively the forming oven. So you've got basically a length of oven, generally gas-fired, working at about between 110 and 130 degrees Celsius, depending on the bico-fibres that you use. And effectively that material is fed through this oven, and during that process the bico-fibre effectively melts, or part melts, and forms a much stiffer, denser product, something that's got a much more resilience in it. If we maybe play video 3 as well, I'll kind of talk you through that. Just you can see the material as it comes out of the far end. You can see clearly before when they moved that with the stick, it was loose. Clearly it's now a mat. It's been formed as a mat. In this case, we were only producing this was a kind of test case. We were producing quite a thin mat, about a 75mm sample. And as you'll see here, it's very easy to cut through it, as the guy will demonstrate in a second. So it's very easy to cut in that length. That's because it's fresh out of the oven. The longer you leave it out of the oven, the more, the tougher, quite frankly, it'll get. The fibres will truly bond and pull it together, which makes it quite not a difficult material to tear, but certainly a little bit more difficult than some striated mineral fibres and other fibres as well. This last image is effectively the kind of finished article, I guess. This is the cashmere insulation. This is kind of Thermobond 1, as we call it. It's the prime product, I guess, that we've developed as a prototype. At this stage, I should mention as well, it's untreated. It's not had anything. It's purely about the bonding technology to this stage. To introduce issues like flame retardancy and insect protection as well. You would treat fibres before you put it through the process, generally. Although we are looking at options to surface treat these fibres as well, and have experimented with that a little bit as well. And at this stage, well, with that first trialling, I guess, and it was still as part of the SMART Award as well, we engaged with Paul at that point. We kind of wanted to know, we knew it was a good fibre, we knew it was a kind of a very high quality fibre, and that it was never really intended that there would be thousands and thousands of tons of cashmere out there. We know there's possibly hundreds of tons potentially, but not thousands. But we wanted to kind of use that trial product at a very early stage to try and understand how density impacted on thermal conductivity, which is really at the heart of this presentation, I guess. And Paul's initial analysis was quite interesting. It kind of demonstrated that with this particular fibre, that there might be an optimised density in terms of the thermal conductivity that we, as architects, I guess, would like to specify. And we got it quite low, but we also understood that we'd made this product as a trial product. It was using particularly good fibres, etc. as well. So, but it was very informative at that stage to try and help us direct where we went next. So clearly, it's not a UCAS accredited result. It's really just a test result, so that we can direct our research going forward. Very, very useful in that respect. Where we went after that was really went, I guess, deep down and dirty, as you might describe it. We started to look into, we knew the wool mills had wool, we knew other textile mills had textiles, we'd kind of steered clear of post-consumer waste, but we started to look at that in a little bit more detail, and that was really the next stage of what we tried to do. Particularly, we were looking at Scottish social enterprises to try and team up with them, because we know at the point of collection of material, and the point of initial processing, it tends to be social enterprises that are involved with that level of work. They're big enough to work with local authorities to win contracts in that sense, but clearly, obviously, because of their employment goals in terms of giving people employment, they're also able to deal profitably with waste at the same time. So we made a few approaches to a few different companies, really with an idea that we would be buying this fibre off them, so we would be hopefully adding value to the supply chain for them as well, and that we could also give them stability in terms of long term, potentially, if this manufacturing plant was established in Scotland. So paper was the kind of obvious one. We spoke to Changeworks in Edinburgh, who deal with about 2,000 tonnes of clean solicitors' paper from Edinburgh every year. They would probably need a little bit of help in terms of how to process that paper into a fibre that was completely useful for this process, but obviously there's a resource there. We also spoke to Springback Mattresses, who have a base in Fife. Quite a dirty trade dealing with old mattresses, but very interesting as well, and there was lots of different waste streams from those mattresses, because mattresses are composite components, composite products. So we'll talk about some of the waste streams in a second that we got from there. Some very interesting stuff. We also spoke to the Forestry Commission about sourcing wood fibre. There's a particular push in Scotland at the moment looking at massive timber construction, and one of the key components of successful wood construction is to have a wood fibre insulation they can use as well. So we looked at that also, and we had a few other different textile streams that we wanted to trial out as well. So really a whole variety of different fibres that we wanted to, in simple terms, just understand about density and thermal conductivity of how these might perform. The first one, let us say, was Thermobond, which is what is on the screen at the moment. An obvious one, I guess you would say, wool. We all know that a woolly jumper works. We know that sheep's wool insulation is a fantastic product and has great qualities. So that was the obvious one. One of the first waste streams that we tapped into with mattresses was cotton. Now, cotton's got a few issues to deal with that wool doesn't. It's clearly doesn't have the kind of innate flame retardancy that wool has. But it gave a very homogeneous product, quite a good looking product, I guess, as well. And what we realised is there was a lot of this type of material available, and also very easy to pre-process in terms of cleaning and tearing the fibre. So we looked at that as a material. We looked at cellulose, so effectively flake paper. We looked at a few different sources of flake paper from different sources. It is quite interesting that what it highlights, and it's an issue in terms of control of manufacture, is the consistency of the fibre that comes through the line as well. That is an issue, but again, it's something that, because it's an open market, you can demand certain specifications of the suppliers, and we would like to think you would put a lot of that onus onto the suppliers of the fibre to meet your specification, or else obviously it doesn't get used. We also looked at denim fibre, so it's really short fibre material, something that the particular process that we are using, this Thermobond airlace system, is particularly good at dealing with very short fibres. It's something that other processes are less capable of handling. They need slightly longer fibres to do it. Clearly, if you can deal with very short fibres, you're into waste that is of less use to other people as well. The longer the fibre, the potentially more use, you might argue, in that fibre. I guess a little bit of a curveball, but we also looked at feathers. In this case, it was nice clean feathers, but in the back of our minds is that there's a huge resource of feathers put to landfill every year. Thousands, tens of thousands, possibly hundreds of thousands of tonnes of barred feathers, mainly from the food industry, food processing industry. And we'd sourced some supplies of that, and it was quite interesting to talk about the economics of that the guys that are processing those feathers are spending money on landfill tax, where they could actually be making a positive by, if they could clean the fibre and pre-process it, they might have a market for that fibre for people to actually buy the fibre from them. So they could turn a cost negative into a cost positive, potentially. So we can erase that with them. And lastly, and I guess lastly in terms of thermal conductivity as well, wood fibre. We know that wood fibre is possibly the worst thermal conductivity natural fibre available. we in this particular product, we used quite, I might describe it as unprocessed shavings. So it was quite large shavings. We knew it wasn't going to be a brilliant thermal conductivity, but again, it was quite interested in that we could bond quite large fibres using the same line as well. So this particular line that we were experimenting with could do, dust in terms of denim dust, and up to about 50, 60 millimetre long, as it happened in this case, cedar shavings, which we were also interested in that as potentially another product that maybe becomes a lining that has obviously a nice aroma to it as well. We also looked at some basic staple fibres, so polyesters effectively. Again, nothing particularly brilliant about those. They've clearly got fire retardancy issues about where you can use those because of the plastic nature of the product, but we were really just experimenting at this stage to kind of see what might be produced. And again, another polyester cotton mix. This is a one from the mattresses. This is a waste stream from the mattresses. So when we are trialling it, I guess we're thinking that, yeah, okay, we know that there's maybe 500 tons of this particular fibre ready to go. So for us at this stage, we're purely testing the manufacturing capability of the fibre. And that's concluded. I'll now hand over to Paul Baker to tell us a little bit more about his results that he got from testing these fibres.
Right. Good afternoon. Well, it was a fairly simple job for us, just using a simple piece of apparatus to measure thermal conductivity. So this is called it's a laser comp, and it's suitable for measuring insulating materials with maximum thickness just over 100 millimeters, and the sample size has to be roughly 300 millimeters by 300 millimeters. It's a heat flow meter, and we use the British standard to perform the tests next stage. And we've looked at these various recycled materials for Bruce. And one feature of the apparatus is that you can you've got movable plates so that you can actually compress the material to different densities, and so you can optimize hopefully the density to look at the optimum thermal conductivity for that particular product. Next slide. So these are the results. I guess most of them kind of cluster around the thermal conductivity of 0.035, and hopefully you can see that some materials is definitely, as you increase the density, you actually significantly improve the thermal conductivity, but there's a cluster of materials that kind of sit around 0.035. So they're quite similar values to some of the what you might call the more conventional insulation products. So you can see there that's the most common materials that are used: glass fibre, mineral wool, expanded polystyrene, but you can see them in that cluster there. But the fibres can't compete, for example, with polyurethane foams. That's essentially in another ballpark. But I think the waste materials generally perform as well, and in some cases better than some of the conventional insulation materials, and I think it's just a case of perhaps further research looking at maybe optimum fibre size, etc., to try to improve some of these materials even further. But I think this work was useful in the first instance in looking at the potential of these materials and at least trying to optimize the density to get the best thermal conductivity. So next. So really, in conclusion, most of the materials have an acceptable thermal conductivity of around 0.035. So compare favorably with conventional insulation materials, and there's an optimum density range of between about 35 and 65 kilograms per meter cube. So the apparatus has been a useful tool for optimizing this density thermal conductivity relationship of these materials. So thank you.
Thank you very much, Bruce and Paul. While we are waiting for questions from our online speakers, and some are already coming, let's see. The first question, it is from Tom Woolley of Rachel Bevan Architects. Have you done any work on the hygroscopic properties of the different materials?
No.
Do you intend to?
Yes, we do. So it would be, I think, particularly now that people are interested in concepts like moisture buffering and dare I say, quote unquote, breathability, etc., then I think it would be, these materials perhaps have the potential for absorbing and releasing moisture, and from past work we've done on looking at the vapor permeability of various materials, including hemp and wool insulation, and comparing it with, say, mineral wool. There tends to be much of a muchness with vapor permeability that we found previously, but I think the difference will come if we actually look at the moisture absorption. Then I think the natural materials will tend to be more hygroscopic than the conventional insulation materials.
I'd add to that as well that certainly from our experience, looking at the hygroscopic nature of the insulation is one part of if it is breathing wall or vapor open technology. It's looking at the whole wall, what makes up the whole wall, especially in terms of timber frame, in terms of sheathing materials, what can actually achieve vapor permeability, because it seems to us as well that there seems to be a little bit of confusion out there about how much that technology actually contributes necessarily to well-being or to humidity effectively in the house in terms of moisture buffering. So we're definitely going to kind of try and research that, but I think it'll probably link on to some of our other research that we'll research it, for instance, in a timber frame panel that we've also designed to minimise things like thermal bridging, and try and get that as effectively a product, a system that we could then potentially offer to the market as well.
It is a question from Jim Monaghan of the Highland Ecology Centre. Did you consider other cellulose-based fibres such as straw or other crop residues?
We didn't look at straw and grass, but yes, it's a good idea. I mean, I've seen some products that use it. I think not that we've necessarily tested flame retardancy, but there are issues that maybe arise from some fibres as well, and how easily we can actually treat them for flame retardancy. But straw clearly would be a fantastic material. Feathers was a little bit of a mad suggestion from the back of the room at one point, and we managed to do that. So there's no reason why we can't use straw.
Yes. Here we have a sample of duck feathers, and also some of the wool.
Yeah.
Could you tell us, is it difficult to source these materials? How difficult?
It's not necessarily difficult. I think in terms of commercialisation, clearly you would need to make agreements with the various fibre suppliers. The interesting thing about looking at waste fibre is that it's an open market. So you've got different, and we found particularly social enterprises that are processing fibres at the base level and then have a product that they're trying to sell to the market. By having a variety of different fibres, clearly we are looking for a flexible input into the process as well. We don't necessarily want to be tied up with one fibre, for instance.
Yes. Question from David Whitelaw of Green Assess. Are any of the materials tested looking more favourably in terms of commercial viability? Which one would you start with?
It's quite an interesting question. We think there's two elements to commercial viability. There's cheaper products and there's premium products, perhaps. And clearly, cashmere is a premium product. There's only so much waste as that. The most basic one and the cheapest fibre is cellulose, i.e. paper. That's the easiest one to get hold of. It's a kind of renewable resource in some ways as well, that it can go back in and it's very biodegradable. We think wood also has got quite an interesting future. It's not necessarily the best conductor, but mixed with the right resins might offer different applications, perhaps, particularly for things like warm timber frames, solid wood construction. We're also quite interested in the dust ones as well, the very, very short fibres, because those are, I guess, the trickiest waste to reuse. They're the ones where the fibres have got maybe less value, perhaps. In terms of viability, all the fibres sourced that we tested are all from Scotland at the moment. We are also quite interested in thinking about how, if you imported fibres, what is the carbon footprint of a fibre from somewhere else, as opposed perhaps road traffic in Scotland. Bear in mind that the bag full of fibres is not a very efficient way to ship fibres, so it has got a carbon imprint on there. That's probably the next part of the research, is to look at that.
A question from George Lomakis of Glasgow, Caledonian University. Did you have any problems with mould developed in the fibres?
No, I should say that, well, the one that we've done the most testing on is the cashmere option. It's been down to the BBA labs for various testing for insect attack, for mould resistance, and for flame retardancy as well. There's a few different options available to treat fibres in these ways. The most common one is effectively a boron solution, a boron salt, which is what most other natural fibres tend to use. They tend to wash the fibres before they use them. There are others available that you might argue are as benign, using various citric bases. We've also engaged with Strathclyde University to look at some other more novel and natural forms of flame retardancy, and which the initial results look quite interesting as well.
During your research, you have probably found out more about whether these materials are used in other countries. What is their experience?
It's very interesting. There's a very successful, I guess, post-consumer installation. Two of them, I think, actually, in America, which they use denim, as you'd expect in America, the home of the jeans, as it were. They produce, again, a very nice product. As far as I understand, that has been tried to be transplanted to the UK, but hasn't necessarily lifted off maybe as much as it should. That was quite a good case study for us, because it raised issues about post-consumer waste. They're also the French, the machines that we were looking at to produce, also have a very good product as well called Limitis, which is interestingly linked to their third sector. So it's linked to homelessness, it's linked with processing clothes. So it would be your Oxfam or your Salvation Army, perhaps. The issue with that is that clearly to use post-consumer fibre is quite not just time intensive, but resource intensive. Simple things like buttons, zips, mess. If someone gives you a bag of clothes and one piece of clothing in there is very soiled, for instance, clearly there's issues there about how you deal with that. That's what we're looking at the moment, is how do you get around that issue, and whether, certainly in terms of process, I think it's better not to try and do that within this process, but to get others perhaps to provide fibre at a specification that you want, and then add value effectively through the supply chain.
Here's a question from Jerry McGuigan of Black Mountain Installation. What price premium would you expect compared to glass fiber? And also, as an architect, how difficult do you believe it would be to convert to natural products?
Hi, Jerry. Good question. Our outset from looking at this, we were kind of always interested, and Jerry will know this well as well, about the price of fibre. What price you buy fibre at clearly affects the end price as well. It varies. The things like the cashmere would probably be in the same price bracket as excellent products like Jerry's product, Black Mountain Insulation, probably in the same kind of area. The cellulose done as a bat might be a cheaper product, but also it might not quite hit the conductivity that compares with other materials. Clearly, mineral fibre is used extensively in Scotland at the moment. That is the predominant timber frame insulation. There are PU foams being used as well, but mineral fibre is the main one. I think there's a lot of really strong arguments about using natural fibre, not least in the retrofit market, in terms of DIY installation. Simple things about not being an irritant, about it being breathable in terms of existing breathable stone buildings. I think there's a great story to tell there. I also think the UK is very well placed. There's a huge market out there as well to get into this. We were talking about it recently at a construction strategy meeting about if we really want to tackle carbon, we'll tackle retrofit. We won't be building zero carbon houses. We'll be trying to tackle the existing emissions. And that's where I think natural fibre, all different types of natural fibre, have a really, really big future, big part to play.
Yes. Here's a question from Morgan Green of CAF. How was this research funded, and what did the application for funding entail? Well, we can say about the application that was submitted to CIC Start Online, which really asked for testing of thermal properties of this material. And since Glasgow Caledonian University has the facilities, then application was submitted jointly by Paul Baker and Bruce Newlands. And funding for this research, for this feasibility study, was provided by European Regional Development Fund and CIC program, up to £5,000 for each application. Currently, we have allocated funding for 50 feasibility studies and 20 academic consultancies. So we do not have currently any more funding through this project. However, Interface is managing, that is organization here in Scotland, is managing innovation vouchers provided by Scottish Funding Council, and organizations interested, or companies interested in applying for research in collaboration with universities can find more information on the Interface website, and then apply jointly with academic institutions to test different products for different products in different sectors. Our project is focused on sustainable building design and refurbishment. So that's a brief explanation how this funding came about. Now we have a question from Dave Tremelin. Is it possible to access a hard copy of the thermal performances of the different materials?
Well, what do you think, Bruce?
Yeah. But I'm not telling you where we've got the fibres.
we could certainly, we're due to write a final report, so we can tabulate the data in that.
To be fair, most of the fibres are generic fibres. They're not. We've sourced them from particular sources, but cotton is cotton. They've got certain fibre lengths, so there's nothing particularly secretive, in that process. I think what we're realising is that a lot of the maybe more valuable knowledge is in the pre-treatment of fibres, looking at alternatives to what is currently on the market. And also just maybe the blend in terms of density, but that's very linked to application, i.e. you want quite a high performance insulation if you're going to put in a wall, because that's clearly going to keep your wall quite thin as well in terms of cost. Whereas in the loft, yes, you can maybe reduce density, worse thermal conductivity, but use more of it because you've got space to use it as well. So that's also something that we are kind of scanning is the applications for these particular products.
Yeah, I mean, I was interested really to find, perhaps it's no surprise, that the thermal conductivity of these various fibres, apart from perhaps the wood shavings, then more or less much of a muchness actually.
Yeah.
I think it's essentially, I suppose, if you think of them all as, maybe it's not so much the fibre as how the fibre traps air,
Yeah.
and there is quite a strong relationship with density, but I think we found, particularly when we did the first trial for Bruce, compressing the cashmere, that there's a kind of point of no return.
Yeah.
So there's no point in trying to increase the density to improve the thermal conduct. I know it sort of goes against the grain to say that as you increase the density, the thermal conductivity comes down. But I think I suppose there's physical reasons why that's the case. And obviously, if you go too far, the thermal conductivity starts to go up again. But I think if you hit a kind of ballpark density range, then you're going to get this sort of 0.035, which is fairly typical of fibrous insulation materials.
It's good. I mean, in terms of mineral fibre, premium mineral fibre is 0.032. All the way through to maybe stuff that you buy at the local DIY store, 0.04. So it's kind of mid-market, you might describe it as. But I think I agree with what Paul was saying. There's still scope there, I think, to look at the fibre blends, possibly the density of binder that we're using as well. There's a few parameters I think we could look at to maybe enhance it even further. That's the next stage, really. So.
Yeah. I think you'd have to do quite a detailed investigation as to why some fibres are better than others, and I think perhaps in the mineral wool glass fibre industry, then because they're sort of starting out with a molten mess, and they can engineer the fibre diameters and lengths perhaps more than you can do with these natural materials. But I think the positive thing is that you're coming up with materials that have quite a good thermal conductivity.
And the variety, you've basically got a insulation making machine that's actually a recycling machine. It's got all sorts of streams going into it to make something that, is pretty basic, but is also, as we know, insulation, pretty damn useful as well. It's the key part, perhaps, if we are going to reduce carbon, it's going to be insulation that does it on a big scale.
So what is the plan now? Future research, then also what do you expect, what will happen, how soon we will see these products just as a regular products in construction being used across Scotland, United Kingdom?
It's a good question. I mean, I think, as Paul says, there's still an element of research to be done in terms of performance, I think. In terms of a commercial endeavour, there's various sources of the material, so there's agreements potentially to be made if it were to go into production. We've all kind of always thought that there's an issue about going to market and that you have to package this, sell it, and go to the public with it. That it seems to me that it'd be much better if larger construction firms, particularly off-site manufacturers, got involved with the process, invested in the line, and actually produced the insulation for their systems. So you're cutting out carbon all along the route, and at the end of the day, architects and clients are getting a better timber frame panel, perhaps, if we can prove the hydroscope that has a impact on the house as well. Apart from that, clearly, as a waste, using waste streams, it's got lots of other benefits as well. In terms of, I'm particularly interested in this idea that social enterprise actually gets value from the fibre. I think there's very few products that can claim that kind of benefit if that can be put in place.
Okay. We have a comment from Dave Traveling, who is saying, thanks for the content and the humor. And now a question from Chris Whiteman, Laboratorio de Energía e Eliminación. On average, what percentage of binder is needed to thermally bind the natural fibers?
It varies on the fibre. To give you an idea, the cashmere one, the final one we produced, the process is quite efficient. It's down to about 5%. Now, most other natural fibres use about between 7 and 10%, and sometimes higher. But things like the wood require as much as 20%. And that's because it was bigger fibres. So it varies in the fibres. Clearly, it's the percentage you want to reduce as much as possible. It's a polyester that we use, but there are PLAs that you can use as well that you might deem more benign, perhaps. PLA, polylactic acid, plastic sorting, man-made or more natural plastics, effectively. But there are issues about the quality of those particular fibres. The bico fibre is the main staple fibre that gets used. And it's interesting, when you look at the machine makers, they are competing with each other to be able to produce products that use less and less of the bico fibre. It's by far the most expensive component of the product. It's usually about 3 times the price of the actual fibre itself.
We have a comment from Tom Woolley of Rachel Bevan Architects. Very useful session, thanks. Please get involved with the ASBP, Alliance for Sustainable Building Products, and look at the Nature Plus certification for any products you produce, and good luck.
Perfect, thanks Tom.
Well, any final comments, any other suggestions or information you would like to share with our viewers?
No, I think Tom's comment there is very useful, and I think if all natural fibre producers come together in those types of ways, I think that's a strong commercial power as well. Maybe change specification habits.
I've just got a question for Bruce, actually. What about blown insulation? Could it be? Is it feasible with these kind of materials?
I think it is. I have been investigating this a little bit. Looking at mineral fibres and beads, etc. There's various forms of loose blown. There's wet blown, clearly with cellulose, and there's blown with a fibre, blown with a binder, sorry, and the binder reacts in some kind of way. I think there might be scope for a dry blown thing. My worry, and it's more from an architect's perspective, would be settlement, especially in timber frames. In loft situations, maybe less so, but I suspect there's something quite good about having it bound as well in a form, or contained in some kind of form. Closed panel would be easy to fill it, evidently. I suspect as well, though, that we might hit even higher densities than what we've been testing, which might actually impede thermal conductivity. But very, very interesting area.
There's certainly a market for that with refurbishments.
Absolutely.
And we've recently been doing some work with Historic Scotland and Glasgow City Council, looking at easy ways of internally insulating tenements, and it's surprising the number of tenements, well, that we've seen anyway, that have studs and plasterboard from the 70s or 80s
inside the face.
and you've got nice 90mm cavities or so. But one of the things is essentially, which is cheap and cheerful, without any major effort, is to blow insulation into that cavity. So, I mean, we're looking at some of the risks that you might get from moisture, etc. But there's certainly a big market potentially for blown insulation.
It touches on treatments as well. I mean, it'd be something we'd be very interested to develop with the wood fibre, and that if you see some products in the markets that use paraffin waxes, for instance, some use beeswaxes, that gives it a resilience against moisture, really getting into it and moulding it. It'd be interesting to look at a coating system, so you could blow those types of insulation into cavities. Equally, though, it is worth, I mean, something that I'm very aware of when we specify blown insulations, that half the cost there is the work, the guy doing it, as opposed to fitting bats for new build is a lot cheaper. But yeah, I think that, as I say, that the retrofit challenges, let's describe them, are actually opportunities for new products, particularly natural fibre products. And it's just about format, I guess.
Jim Manahan of the Highland Ecology Centre agrees with you regarding settlement problems with blown fibres. But there is an interesting question from Harry Phillips of Holmes Wheeler Ltd. Can you find a use for Japanese knotweed?
Excellent question. The ultimate waste.
Is it a biofuel?
Yeah, I'm sure we can. I mean, I'd put that in the same bracket as straw. Why not? Why not?
Then a question from George Lumakis of Glasgow Caledonian University. Have you thought of the alternative to use feathers instead of wool? That could prove beneficial for poultry farming, as you mentioned in your presentation, I think.
We've feathers is the most recent one. It's interesting. I think there's a little bit of work to be done in terms of pre-processing feathers. You're absolutely right, George, that there's huge amounts of wet feathers out there that are being landfilled. The trick is to clean them, dry them, and what we're looking at the moment is taking the quills out of the feathers and just using the actual feathers themselves. We've seen products produced like that are incredibly homogeneous. Paul's results revealed that, as you might expect, feathers are an excellent natural insulation. They're maybe perhaps been optimised over millennia, possibly even more than millennia, I dare say, to work as insulation. So yes, I think there's an interesting thing. It's something that kind of came up in our mind, and it seems kind of counterintuitive that we were a bit worried about whether people would accept the idea of feathers as insulation. But as we know, we generally all sleep right next to them in terms of pillows and duvets, but there's a degree of abstraction there that you don't see the feathers. So if you see them, I think it might have a bit. But a very quick product that we made. I mean, it's a very first trial, but yeah, we'll definitely be exploring that further. I think there's real potential there.
Okay. There are no more questions from our online viewers. So if you don't have anything else now, we will close our webinar. I would just like to draw attention of our viewers to our forthcoming events. The next webinar that we will have is on 13th of April, that's Friday, and the title is Implications of Installation of Solar Photovoltaic Panels on Properties of Fairfield Housing Cooperative. This is a study that was undertaken by Glasgow School of Art and Edinburgh Napier University. Then on 18th of April, we will have a live conference whose title is Micro Renewables for Buildings and Transport, Deliverables and Barriers. This conference will take place at Edinburgh Napier University. To briefly provide a summary and rationale for this conference, I would just like to say the following. From 2013 to 2020, the next 7 years represent a key stage in Scotland's ambitions to reduce greenhouse gas emissions and improve energy efficiency. The second stage of the Sullivan Report for the 2013 energy standards in new buildings will be due for consultation this year. The finer details of the Green Deal will come before Parliament for enactment in 2012-2013. The changes in transport mode, future fuel systems, electrification of cars or alternative energy systems, and the future turnkey infrastructure required are reaching key milestones in research and development. This conference will address some of the opportunities, challenges, and advancements being undertaken in these areas. The range of speakers from universities and companies will provide useful insights to current and possible future states of play. There will be no live stream from this conference. It will not be transmitted online, and if you wish to attend, you can register to attend in person on our website. So please access www.cicstart.org to see the conference program and book your place today. And finally, on 19th of April, we will have a webinar on benefits and options for retrofit of an 18th century traditional Scottish house using the Passive House standard. This is a study undertaken by Edinburgh, Napier University, and SA Estate. I would like again to thank our speakers today, Dr. Paul Baker of Glasgow Caledonian University and Bruce Newlands of Kraft Architecture, and we look forward to welcoming you at our future events, and thank you for watching.